Hello everybody, lesson 8, topic electronic distance measurement. About history of EDM, electronic distance measurement. Electronic distance measurement first introduced in the 1950s by Gediometer and Company. So development of this type of technology started during Second World War with the development of radar, radio detection and ranging. What is the function of radar? It returns the distance to an object and later versions the speed of the object through the Doppler shift by timing the length of time there from the transmission of a pulse to its return. Accuracy was set by timing resolution. 1 millisecond equals 300 meters. Gediometer, geodic distance measurement, was introduced in 1949 by Dr. Erik Bergstrand from Sweden. This instrument, geodimeter, used light 550 nanometer wavelength to measure geodetic quality distances. Instrument weighed 100 kilograms. We know that first introduced this device in late 1950s. At first, they were complicated, large, heavy, and suited primarily for long distance. And now EDM use either infrared light waves or microwaves, radio waves. Microwaves require transmitters and receivers at both ends. So infrared use a transmitter at one end and a reflecting prism at the other, and are generally used more frequently. About distance. Infrared and laser EDM instruments come in long range, 25 kilometers at night and 10 during daylight. EDM instruments can be mounted on the standards or the telescope of most theodolites, and additionally they can be mounted directly in a tree branch. So greater range during daytime was achieved by using radio waves. And in South Africa, Dr. Wedley introduced the teleometer in 1957. Instrument used X-band radio waves and receive and transmit ends looked similar. Receiver actually transmitted the signal, and Gediometer used one or more corner cup reflectors. And distance up to 50 kilometers could be measured in daylight with this instrument and later models. So about properties. EDM come in long 10-20 km, medium 3-10 km and short range 0.5 3 km. Range limits up to 50 km. They are typically mounted on top of a theodolite but can be mounted directly to a bridge. So, total station equals theodolite with built-in EDM plus microprocessor. Classifications. Described by a form of electromagnetic energy. First instrument were primary microwave, and present instrument are some form of light. That is laser or near-infrared lights. Described by a range of operation. Generally, microwave are 30-50 km range and developed in the early 70s and were used for control surveys. And light EDM generally 3-5 km range, used in engineering and construction. First units circa 1959, 50 kilograms each for measurement unit and optics. A very heavy instrument. And this is example of later model geodemeter circa in 1966. This is the front and back views of this device. This is a teleometer, example of circa 1962 model, back and front of instrument. 9 kilograms with the case. And modern version. This type of measurements are now directly built into the telescope. Assembly of theodolites, and you can see this on most construction sites. The angles are now also read electronically compared to glass optical circles. This is a modern example in 2000. Corner cube reflector, infrared light source used here. About distance and other properties. So EDM is very useful in measuring distance that are difficult to access a long distance. So we have transmitter and reflector, and it measures the time required for a wave to send to a target and reflect back. Current EDM instruments use infrared light, laser light or microwave. So the microwave system uses a receiver transmitter at both ends of the measured line. Whereas infrared and laser system utilize a transmitter at one end of the measured line and a reflecting prism at the other end. Some laser EDM instrument will measure short distance until 350 meters and without a reflecting prism, reflecting the light directly off the future, including building wall being measured. Principle of electronic distance measurement. This figure shows a wave of wave light, lambda, where wave is traveling along the x-axis with a velocity of 299,792 kilometers by second in vacuum. So operation, a wave is transmitted and the returning wave is measured to find the distance traveled. This is returned energy, and this is a modulated electromagnetic energy. So we understand that modulator electromagnetic wave leaving the EDM instrument and transmitted energy to reflector and being reflected light wave or retransmitted microwaves back to EDM, transmitted energy and returned energy. About frequency of the wave is the time taken for one complete wave length. So wavelength in meters equals velocity in kilometers by second, divide second, and this velocity divided by frequency in Hertz. This is a 1 cycle per second. So travels based on following relation you can find by this formula. Intensity modulate electromagnetic energy to specific frequency. Here you can see a Trimble total station. That includes the choice of the integrated cis-ELTA control unit, detachable gidiometer control unit, or handheld TSC date collector, and a wide range of software options. courtesy of Trimble Geomatics. So, you already seen that the double distance 2L is equal to a whole number of wavelengths n multiply lambda to wavelengths plus the partial wavelengths. So distances determined by calculating the number of wavelengths traveled. Yes, so number of wavelengths n multiply lambda and plus the partial wavelengths and divide by 2. Errors are generally small and insignificant to short distances. For longer distances, they can be more important. Important errors can be accounted for manually or by the EDM if it has the capability. And you must understand that velocity of light can be affected by temperature, atmospheric pressure, and water vapor content. So, to understanding about modulated electromagnetic wave and the principle of electronic distance measurement. This is a station, this is a target. And a reference plan within the distance matter for fast comparison between transmitted and receiving wave. And this here a reference plan for the reflection of the wave transmitted by the distance meter. And L a distance. And this is a wave. And this is a fraction to be measured of a whole wavelength of modulation. So here you can see EDM characteristics. This is a 750-100 meters range. Operating temperature between -20 to +50 degrees centigrade. Accurate up to ±5 millimeter, +5 ppm. 1.5 seconds typical for computing a distance and 1 second when tracking. Slope reduction either manual or automatic. Some average repeated measurements. Signal attenuation and battery operated and can perform between 350 and 1400 measurements. Accuracy. Distance is computed by numbers of wavelengths generated plus partial wavelengths divided by 2. Standard or random errors are described in the form of plus minus constant plus parts per million. Constant is the accuracy of converting partial wavelengths to a distance, and parts per meter per million is a function of the accuracy of the length of each wavelength and the number of wavelengths. So idiom accuracy, you can see on the table of errors tabulated our distance, where errors is 5 millimeter plus 3 parts per million. Parts per million. So for distance 10 feet, errors this and linear precision, and parts per millions 1670, etc. About errors and accuracy. Idiom instrument accuracies are stated in terms of a constant instrumental error and a measuring error proportional to a distance be measured. So typically accuracy, you already know. Both the prism and idiom should be corrected for off-center characteristics. The prism instrument constant about 30 to 40 millimeters can be measured by measure AC, AB and BC, and then constant AC minus AB and minus BC. So instrument or prism constant value can be field checked in the following manner. A long line more than 1 kilometer is laid out with end station and an intermediate station B. The average distance AC is measured along with partial lengths AB and BC, and the constant value will be present in all measurements. Alternatively, the constant can be determined by measuring a known baseline if one can be conveniently assessed. And about blunders. What blunders can be when you use idiom and you find a distance? Incorrect math settings, incorrect scale settings, prism constants ignored, and incorrect recording setting. including horizontal vice slope. So this is very important, and you must understand and remember this all time. So, source of error in EDM. Personal. Careless centering of instrument and or reflector. Faulty temperature and pressure measurements. Incorrect input of T and P. Instrument not calibrated, very important. Calibrate in time. Electrical center. Prism constant. Natural. Varying met along line. Turbulence in air, etc. So, determination of system measuring constant. Measuring AB, BC, and EC. Then, AC plus K. K represents the prism constant. So, AC you can present like AB plus BC and plus K plus K. So K will be AC minus AB plus BC. If electrical center is calibrated, K represents the prism constant. Good practice. Never mix prism types and brands on same project, and calibrate regularly. Systematic errors, all instrumentation errors. Microwave. Atmospheric conditions include temperature, pressure, humidity, must have wet bulb and dry bulb temperature. Multipass. Reflected signals can give a longer distance. Light. Include atmospheric conditions, this is a temperature and pressure, and prism offset, include point of measurement is generally behind the plumb line, and today usually standardized as 30 millimeters. About EDM instrument operation, setup. EDM instruments are inserted into the tree bridge. Set over the point by means of the optical plant. Prims are set over the remote station point. The EDM turned on, and the height of the prism and the EDM should be measured. Aim. The EDM is aimed at the prism by using either the built-in sighting device on the EDM. Telescope. Yoke mount EDM will have the optical line of sight a bit lower than the electronic signal. When the crosshair is sight on target, the electronic signal will be maximized at the center of the prism. Set the electronic signal precisely on the prism center. Measure. The slope measurement is accomplished by simply pressing the measure button. Display are either liquid crystal or light emitting diode, LCD or LED. The measurements is shown in 2 decimals of a foot or 3 decimals of a meter. EDM with the built-in calculator can now be used to compute horizontal and vertical distances, coordinate atmospheric curvature and prism constant correction. About record. The measured data can be recorded in the field note format, can be entered manually into electronic data collector. And very important that the distance data must be accompanied by all relevant atmospheric and instrumental correction factors. Uses. Total stations are ideal for collecting a large number of points. Topographic and as-built, monitoring and control, construction layout. They are commonly used for all aspects of modern surveying. Only when harsh conditions exist or distances are short will a transit and tape be used. And about disadvantages. Total stations are dependent on batteries and electronics. The LCD screen doesn't work well when it is cold. Battery life is also short. Total stations are typically heavier than a transit and tape. Loss of data is an important consideration. So you already know uses and disadvantages of EDM and understand about properties and principles of electronic distance measurement. So you must understand, for a civil engineer, there is no such thing as a little mistake. Thank you and bye.